this all looked very nice in the 70s. The problem was that it was not very nice. In the 70s, they just had no chance to sort out why it wasn't nice, because the measurement equipment was not good enough. But after a little while, designers and researchers found out why a tube amplifier always sounded better than a transistor-based amplifier in the 70s and 80s. Almost always, at least. I'm sure somebody debated. Some people said that CD sounded better than LP in the 1980s as well. I did, but I know I was wrong now. The problem's name was distortion. And it seemed that in this process of amplification, the amplifier stage with the amplifier made its own sounds. It made copies of the original sound you wanted. One thing that Scandinavian person found out was well, it doesn't really matter what it's called, intermodulation distortion. I'll write it anyway. Let's say that, new graph again, we'll soon end. This is amplitude or volume, how loud you play. This is frequency, meaning how dark or bright the tone. Intermodulation distortion is a form of distortion where the amplifier just makes what looks like random copies of this original tone. And the practical effects of that was that when you wanted to reproduce this, what you heard was the sum of this plus many other sounds, smear. You cannot hear that one tone as clearly as you wanted. Another form that was, or is, very bad is called harmonic distortion. The list goes on, but I will explain one more. There are several, and it takes too long. Let's say again, amplitude or volume and frequency. Adnan says you rarely do technical presentations here, so this could be the first. Oh, well, let's say you want to play a clear tone, and to make the example easy, 1000 hertz. The amplifier will make a copy, so this is 1000 hertz, at exactly 2000 hertz. 3000 hertz. It's like hitting 3 keys on the piano right next to one another. It's not that bad. It creates ambience and it's not correct, but it doesn't sound bad to the ear. Tube amplifiers are known to have a lot of distortion. What they have is this, harmonic distortion, and they only have what we call the second and the third harmonic. Meaning they can have a lot of it, but it still does not sound bad to the ear. The problem with transistors is that they don't stop there. They continue with a 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th harmonics. And suddenly you're not hearing 2 keys next to one another. You're hearing some keys here and a disharmonic key over here. That make amplifiers sound harsh. And you're, oh my God, you just want to turn the volume down. And, you know, there are other types of things, like crossover distortion, and there's transient intermodulation distortion, and so on. Now, this was only discovered throughout the, well, perhaps something was discovered in the late 70s, but I would say throughout the 80s and beginning of the 90s. And the essence here was that this feedback that they designed, when they didn't know about this, was made to make a stable amplifier. Then the problem came when they realized all these artifacts were created in the amplifier, and you were shipping some of the output to the loudspeaker back to the beginning of the amplifier. You shipped all these things back to the beginning and then run them through the amplifier to make them bigger. So transistor amplifiers sounded to some degree awful in the 70s and the 80s, unless they did something to just make it smoother. But this was very bad in any case, and the amplification of the distortion was very bad. So the solution in the 90s was that they reduced the use of feedback. Some call it zero feedback amplifier. I don't think they do anymore because it's not true. You need some feedback or the amplifier would oscillate. But you used less of it and got less distortion and smoother sounding solid state amp. And in the end, you would see, if you look at the catalog from the 80s, oh my God, I've used my 10 minutes and more, you would see technical specification of JVC, XLV, 1011, something, total harmonic distortion, 0.011%. Damping factor, 140. Then you go to 2017, and you look at 80% of the catalogs, and you see technical specification, total harmonic distortion, 0.00007%. It's a lot lower. And then you look for damping factor, and you can't find it. Because damping factor, it's called a lot of things from salespeople who want to talk about damping factor. It's called, oh, it's damping factor explains bass control. No, it doesn't. But the effect of what it does is better bass control. It explains the stability of the amplifier. How stable is it? When I play music to the loudspeaker kicks this power back to the amp. And the amp must be stable to stop this return kick. The ability to do that is measured in something called damping factor. What Bent, our founder, saw, and that inspired the beginning of HEGEL, was that there is a trade-off here when you make an amplifier. You could either use little feedback and get a smooth and natural sounding amplifier, but it would lose bass control. Or you could use a lot of feedback and get a very stable amplifier, but it would sound harsh and unpleasant in comparison. So he made them with high damping factor because he made them for a live stage. And you can just tweak it on the equalizer board to make it sound soft again. You can't do that at home. But this whole concept led to an idea in the master paper about a different way of solving this issue. And then he graduated from the school and did his master degree in 1990. He didn't get anybody really interested in his ideas. So he started working for a Norwegian company called Tandberg for a little while. Then he worked as a transistor designer for a while. He worked as a chip designer for a little while. But eventually, in the beginning of the 90s, he got a big investor that saw opportunity in this. And the investor is now the 5th or 6th biggest telephone company in the world.